Heaps and priority queues. One warning before we start. The word heap also means the area of memory where new objects are stored. That is not this. This heap is a data structure, and it does one job. It always hands you the most urgent item next.
Here is where this bites in real code. You run background jobs, nightly reports, welcome emails, invoice files, password resets. For a long time, you take them in the order they arrived, and that is fine. Then the queue gets long. One night, there are 100,000 jobs waiting, and 12,000 of them are nightly reports. A password reset lands at the back. The user is sitting there waiting. The report is not. So you change the rule. Every job gets a number for how urgent it is, and you always take the smallest number first. That rule is easy to say. Finding that smallest number over and over again is the part that costs you. So this is the subject, a priority queue. It is a promise about behavior. Items keep arriving, and whenever you ask, you get the best one out. Under that promise sits the structure we are going to build, a binary heap. It is the standard way to keep that promise cheaply. There are only two moves in the whole structure. One is called sift up, and it runs when you add something. The other is called sift down, and it runs when you take something out. There is one more trick, called heapify, which turns a list you already have into a heap in a single pass. That is the whole syllabus. 4 ideas. Not sorting, and not search trees.
Before any code, one picture, because there is a confusion worth killing early. On the left is a bakery. You walk in, you take a numbered ticket, and the counter calls the numbers in order. That is a plain queue. It never asks why you came. If you are in real trouble, you still wait behind everybody else. On the right is a hospital. The same 5 people walk in the same order, but a nurse at the desk gives each one a severity from 1 to 5. The chest pain goes through the door first, the sore throat goes last. Now look at what the nurse did not do. She never put the whole waiting room in order. She keeps exactly one fact ready at all times. Who is worst right now? That is a priority queue, not a sorted room, a desk.
Let us build it the obvious way, twice. The first way is a plain list. Adding a job is easy. You put it on the end. Choosing is the problem. To find the most urgent job, you call min, and min looks at all 100,000 jobs. Then you remove it, and remove walks the list again to find it. 2 full passes every single time you want one job. The second way flips it around. Keep the list sorted, so the most urgent job is always at the front. Now choosing is free, but adding is not. Finding the right spot is fast. Making room for it is not, because every item after that spot has to shift over by 1. One way is cheap to write to and expensive to read from. The other one is exactly the opposite.
I ran both of them on this machine, with 100,000 jobs, draining the whole queue. The plain list with min took 72 seconds, not milliseconds, 72 seconds to work through 100,000 background jobs. The sorted list took 1.39 seconds. That is much better, and it is still not good. It is 25 times more than the third option spends. A binary heap did the same work on the same machine with the same answers in 54.8 milliseconds. 55 milliseconds against 72 seconds, about 1,300 times faster. And all of it comes from one decision: stop keeping everything in order.
Here is the idea, and it is smaller than most people expect. Draw your items as a tree. Every circle holds one value. Now the rule, and there is only one rule. Every parent must be smaller than or equal to both of its children. That is it. That is a heap. Read that rule again, and notice what it does not say. It says nothing about 2 nodes sitting next to each other. Look at the bottom row here. 12 sits to the left of 8. 12 is bigger than 8, and it is completely legal, because those 2 are not parent and child. So a heap is a very weak kind of order, and that weakness is exactly why it is fast. The only thing you get for free is the smallest value, sitting at the top. Now the second half of the idea, and this is the part that makes it cheap. There is no tree. There are no circles. There is a plain list. Take the tree and read it level by level, top to bottom, left to right. Write those values down in one flat list, in that order. That list is the heap. The tree was only ever a picture we drew to explain it. Watch the highlight walk along. Index 0 is the root. Its two children are index 1 and index 2. And from any index, you can compute the whole family with arithmetic. The parent of index I is I minus 1 divided by 2, rounded down. The left child is 2i plus 1. The right child is 2i plus 2. Three small sums. No pointers, no node objects, and no memory for the tree at all.
Here it is in code. 3 functions of one line each replace an entire node class. There is no class with a left field and a right field. When you want to know who sits above index 7, you do not follow a pointer. You compute 7 minus 1 divided by 2, which is 3. The last function is worth keeping around. It checks the one rule across the whole list. For every index except the root, the parent must not be bigger. And look at the output. That list is a valid heap. Sort the same list and you get a different list. So say it out loud once. A heap is not sorted and it is not trying to be. It only knows which way is down.
Now the first of the two moves. You add a job. Watch the picture. The new job has urgency too, which is very urgent, and it just lands on the end of the list at index 7. So we fix it, one step at a time. The parent of index 7 is 7 minus 1 divided by 2, which is 3. Index 3 holds 9. Is 2 smaller than 9? Yes, so they trade places. Now our value sits at index 3. Its parent is index 1, holding 5. Is 2 smaller than 5? Yes, trade again. Now it is at index 1. Its parent is index 0, holding 3. 2 is smaller. Trade one more time. Now it is at the root, and we stop. 3 swaps for 8 items. And notice what we never touched. 12, 8, 14. We never looked at them once. The value only ever compared itself with its own parent.
That walk written down is this. Sift up takes a list and a position. While that position is not the root and the value there is smaller than its parent, swap the two and move up to the parent. The loop stops for one of exactly 2 reasons. Either you reached index 0 because you are the smallest thing in the whole heap, or your parent is already smaller than you, which means the rule holds again everywhere. Push is then 2 lines. Put the item on the end of the list, which is cheap, then sift up from that last position. The cost is at most 1 swap per level of the tree. In a few minutes, we will count how many levels there actually are.
The second move is taking the most urgent job out. The answer itself is free. It is always at index 0. Here it is a 3, and that is the job we run. But now there is a hole at the top, and a heap has to stay a complete tree with no gaps in it. So we take the very last item in the list, the 14, and we drop it into the hole. So we sink it. The children of index 0 are index 1 and index 2, holding 5 and 7. We swap with the smaller of the two, which is 5. Now our 14 is at index 1. Its children are 3 and 4, holding 9 and 12. The smaller one is 9. Swap again. Now it is at index 3, and index 3 has no children, so we stop. 2 swaps. And that word smaller matters. Swap with the bigger one and you have just put a large value above a small one, which breaks the only rule the heap has. Sift down looks at a position and at both of its children. It picks whichever of the 3 holds the smallest value. If that is the position we are already at, then nothing below us is smaller, so we are done and we return. Otherwise, we swap with that smallest child, move down to it, and go round again. The 2 length checks matter. A node near the bottom may have 1 child, or no children at all, so we always check that the child index is still inside the list before we read it. Pop then reads almost like English. Take the last item off the end. Remember what is sitting at index 0, because that is the answer we owe the caller. Put the last item into index 0. Sync it. Return the answer we remembered. So both moves walk 1 level at a time. The obvious question is, how many levels are there? A complete binary tree doubles at every level. 1 node, then 2, then 4, then 8. So the number of levels is the base 2 logarithm of the number of items. In plain words, that is how many times you can have the number before you reach 1. For 1 million items, that is 19 levels. For 1 billion items, it is 29. Read those 2 numbers next to each other. You multiplied your data by 1,000, and the work per operation went up by 10 comparisons. Not 10 times, 10 comparisons. That is what log n buys you.
and it is why this structure does not care how big your queue gets. Now the move that surprises people. Say you already have a list of 1 million jobs and you want a heap out of it. The obvious answer is to push them in one at a time. Instead, start at the last node that actually has a child, which is halfway through the list, and walk backwards towards the root, sifting each node down. Here is why that is allowed. The second half of any list is all leaves. A leaf has no children, so it is already a legal heap of one item. So we skip all of them and start in the middle. And here are the counts, on 1 million items in the worst possible order. Building bottom up took just under 1 million swaps, which is 1 swap per item. Pushing them in one at a time took nearly 18 million, which is about 18 swaps per item.
1 swap per item against 18 swaps per item. On the clock, that was 21 milliseconds against 323, about 15 times faster. When you push items in one at a time, a new item can climb the full height of the tree, so each of the n items can cost you log n. When you build from the bottom up, that is not what happens. Half of all the nodes are leaves, and a leaf cannot sink at all. It costs 0. A quarter of the nodes can sink 1 level, an eighth can sink 2. Only the single root can fall the whole way. Add up nodes times distance across every level, and the total settles at about 1 times n. That is linear, not n log n.
Now the honest part, because this is where people get hurt. A heap answers exactly one question. What is the smallest thing you are holding? It is not a sorted list, and you cannot read it in order without emptying it. Finding a specific item by name means scanning the whole list, which is the exact cost you came here to avoid. There is no cheap way to delete one job in the middle or to change a job's priority after you have queued it. And even the second smallest item is not simply at index 1. It is at index 1 or index 2, and you have to check both. If you need any of those things, you need something beside the heap, like a dictionary from job name to position. Reaching for a heap and then searching through it is the mistake this part exists to stop.
3 guards you need before this ships. First, ties. You push a job as a pair, the urgency, then the job. 2 jobs at urgency 5, and Python compares the urgencies, finds them equal, and then compares the jobs themselves. If your job object has no ordering defined, that is a crash. The fix is a counter. Push the urgency, then a number that only ever goes up, then the job. The counter can never tie, so equal urgency means first in, first out. Second, you often want the largest, not the smallest. Do not write a second heap. Negate the key on the way in and negate it again on the way out. Third, the top 10 of a stream that is far too big to store. Keep a heap of exactly 10. If a new value beats the worst of your 10, swap it in and drop the old one.
And now the part that makes this worth knowing. You have almost certainly used one of these already, under a different name. Task schedulers use one to decide which job runs next. Timer systems use one to find the deadline that expires soonest. Dijkstra's algorithm and A*, the shortest path algorithms behind map routing and game pathfinding, are both a priority queue with a graph attached. And here is where you will write one yourself. Top K over a stream. Cache expiry, deciding what dies next. Retry queues, deciding which attempt is due. Anything at all where the words are, handle the most important one first. Python calls it heap queue. Java calls it priority queue. Go has container heap. C++ has priority queue. Same structure, same 2 moves.
If this comes up in an interview, these are the 3 questions, and here is the shape of each answer. Why is a heap not just a sorted array? Because a sorted array pays order n on every insert, since everything after the new item has to shift over. A heap only ever orders a parent against its own children. Why is building a heap order n and not n log n? Because half the nodes are leaves and cannot sink at all, and only the root can fall the full height. Sum up nodes times distance and it converges to n. How do you get the largest instead of the smallest? Negate the key, or wrap the item in a class with reversed comparison. Never keep a second heap in sync with the first. All 3 answers come from one picture, the tree above and the same list below. If that filled in a gap, hit like and subscribe. This is the Missing CS degree, 1 unit at a time. Thanks for watching.